All right, hi, I'm Jonah. I am not from Finland, but I am enjoying being here. This is the opening of StanCon Helsinki, or at least the workshop part. How many people here are not from Finland? Oh, wow. Okay. Well, I was going to say that's amazing, but I don't want to insult the Finnish. I just mean it's so cool that people are coming all the way over here from so far away. All right, so here's what I'm just give you a little bit of the plan for this. This is a really kind of challenging thing where we're supposed to kind of introduce Stan and also make sure people have some of the concepts that you'll need later on, and do that all in like 3 hours with a little coffee break in between. And so I'm going to tell you right now, we're going to fail at that. But my hope is that it will give a little bit of a foundation for those of you who haven't used Stan before to then pick it up yourselves with a little stronger footing. And for those of you who have, and for which all of this is review, then maybe I'll give you a slightly different perspective than you've heard before. And so we have, welcome. If you're just coming in and you have a computer, there's a link to download some stuff at. So this is Lauren, who helped prepare the materials here. You did? Yeah. And this is a thing that if you have a question, there's actually a microphone in here, and she'll toss it to you, and you can speak like into the box. Apparently.
Yeah, so apparently they developed this at Aalto uni, I think. That's what Aki tells me.
That's a Finnish thing?
Yeah, and the microphone turns off when you throw it so you don't get wind noise, which is just so cool.
All right, so if you have questions, please stop and ask questions, and if you're worried that you can't project loud enough, we'll toss you the, the catch box or whatever it's called. All right. Has everybody had a chance to go to that link? Can I change the slide? Ready? Okay. I'll come back to it in a second. Okay, so I also wanted to get a sense, are people here in this workshop, the introductory workshop, because you're totally new to Stan, or because you are kind of exploring it a little bit and want to hear from some of the developers, or how many people here have never saw a single line of Stan code or even know what it? Okay, so a few. All right. Well, you're not required to have seen a line of code, but it is encouraging to see all that so many people have. All right, so here's where I'm going to start. Stan was maybe a poor choice of software name, because if you used to Google it, you'd get pictures of South Park characters or Eminem videos, because he has a song called Stan. And so, but now I think we're finally creeping up onto the first page of Google results, even if you turn off, if you go on somebody's phone who's never searched for a single statistical thing in their life. We finally, I think, made it onto the first page, but we're still kind of behind these guys. So, but this is Stan, the physicist and mathematician, who the reason we named it after him was because he was foundational in the development of the Monte Carlo method, which we'll talk about. And for better or worse, he's also known for the hydrogen bomb. That's not why we named it after him, but like many other people who have made contributions to things that we're doing now in Bayesian inference, a lot of it came from physicists and mathematicians working on government and military projects, and we've kind of taken their ideas and tried to do other things. This next slide has a decent amount of text on it, and most of it's there for you to kind of go back through afterwards and click on some hyperlinked stuff. But to give you just a general overview, and I want to emphasize this, is Stan is a language and then it's also a set of algorithms. It's not something where those two things are enmeshed together. It's something where you'll write something in the Stan language and you can choose different algorithms to run that model, right? You can choose MCMC, which is what we're gonna emphasize here, but there are there are approximate algorithms that you can run, and this conceptual separation between being able to express a model and then letting people who have written these algorithms kind of take care of fitting that model for you is what we're trying to go for, to allow people to write down models and not have to be writing the algorithms themselves. But there really is this conceptual distinction there where we can say, hey, write down a program and then choose from algorithms that will fit that program for you, and you don't have to change the way you wrote the program, right? Okay, and so again, some of these are just for reference afterwards, but the distinction here is that there's a program. So you don't have to worry about all these like acronyms and things, but the distinction here is that there's a program and then we'll perform inference, right? And these are related ideas, but you can think about Stan as a language, and then you can separately think about making inference using that language to express a statistical model. And we'll see examples of this. And then in particular, these are all hyperlinks. So I'm gonna put the slides up after this. So I'm not going through these one by one, but I want you to be able to go back and click on these links. Stan is also an ecosystem where there's lots of packages and different platforms and interfaces and developers and users and people developing software packages, but also tutorials and case studies and discussions on the forums. And so I put up a bunch of links on here that I'll give you in the slides so you can go through and take a look at the different kinds of things that make up the Stan ecosystem. Cool. And so then what I want to do in the little bit of time we have today is I'm going to talk a little bit about what is like a Bayesian workflow, right? Why are you doing this in the first place? So what does something like Stan, what kind of workflow does using a tool like Stan allow you to do, and why do we care about that? And then we'll get our hands dirty and actually write some pretty simple Stan code, because I'm not assuming you've seen it before, but and so we'll see how far we get. I've put online, in that repository, a markdown document that's actually really long, and we're going to get. There's like the second half is commented out. I'm not even sure we're going to get through the part that's not commented out. The point there was so that you could later on go through the rest of the document on your own, because it really is a full document, and we're just going to get through the beginning section and write the simpler models. But you'll be able to then on your own later see how the rest of the stuff goes forward and the models become more advanced. So if you go to the hierarchical modeling class this afternoon, then some of the later models in the document that I posted online will make more sense, but we'll do the beginning section of it. Does that make sense? So I'll do like a little bit of lecture on workflow, and then we will jump into some programming. Right? And so some of my colleagues recommended to me, so I've been myself and Dan Simpson and Aki, who is the organizer of this conference, and Andrew Gelman and Michael Betancourt, I've been thinking and writing about how do you think about Bayesian workflow, and we wrote a paper on the role of visualization in that workflow, and so I'm going to use that as kind of the basis for talking about the workflow, but showing pictures as a large part of it. So how can we see a Bayesian workflow visually so that I don't have to put a ton of math on the screen right now at 8:30 in the morning? All right. There's just going to be a little bit of text and a little bit of math, but for the most part, this is really just conceptual, and then we're going to get into the software part and see how this actually gets implemented when you go work on something. Okay? And so we're going to talk about exploratory data analysis. We're going to touch on this very lightly, but it's a little bit different than just like looking at your data. We're going to talk about it in the context of already starting to imagine models that you might be fitting to your data, right? Then we're going to talk about something called prior predictive checking, which really doesn't get talked about that much, or at least not until somewhat recently, which is this idea that even before you fit your model to data, right, the kinds of models we're gonna write are going to imply certain data generating processes. They're going to imply certain types of data that you would see if the model you wrote down, were reasonable. And even before you fit your model to real data, if the model that you wrote down in code, right, simulates unrealistic data, then it's probably a sign that it's not even worth fitting it to your real data. You haven't developed some kind of model that's consistent with your scientific knowledge or whatever your domain expertise is, right? So we're going to see an example of that in a second. And this relates to thinking about what are the implications of the choice of prior distributions. And the way to really see that is by thinking about what the implications are for the data that a model might generate, right? Then you have to like fit a model, right? And there's all sorts of algorithms and diagnostics, right? We'll talk a little bit about the MCMC algorithms, but we're not going to do a deep dive, unfortunately, because it's a short morning. Right, but after you fit your model, then you kind of repeat this process that we did originally when we first asked, well, is our model realistic based on our current knowledge of the world, like before we fit our model to our real data? And then we can ask, okay, after we've learned from the data that we do want to fit our model to, right, is what we've learned consistent with what we observe about the world, right? And that's the difference between the prior and the posterior. One is thinking before we've updated our beliefs based on the data that we've collected, what does our model say about the world? And then after we've done that, what does our model say about this, in some sense, the small world that we've chosen to construct here to study, but depending on how far out you want to go in using your model, how far you want to extrapolate outside of the narrow range of what you're doing, right? It's going to become more and more important what kinds of data your model really can simulate. And that's because that's ultimately what Bayesian modeling is about. It's about models that can simulate data, right? This is often referred to as a generative model. And we'll talk about this soon, but upcoming in the slides, but I want you to already start thinking a little bit about what does it mean for like a model to be able to simulate data. It's going to mean that we need to mathematically describe a process that could have resulted in the data that we observed, right? And so we'll see that concept keep coming back over and over and over again in each one of these phases. It's going to be relevant. And then Aki is going to talk about it this afternoon. We're not going to get to it in this class, but it is an important part of the workflow, is model comparison, model selection. How do we compare models on criteria that we care about, right? And again, I'm going to post all these slides afterwards, so you'll all have all this stuff. Okay? So I see some people taking notes. You do not need to write down the contents of the slide, but if you do have other things here, feel free to. Okay. So in the next little bit, I'm going to talk about these first couple sections. And we'll start writing some code, and then we'll come back and talk about like the second half of the workflow, right? We'll talk about the workflow up to fitting the model, then we'll stop and think about, all right, how do we fit a model? And then we'll come back and talk about, all right, now what do we do with the fitted model? All right? And I think this stuff is a lot easier to understand if I give you a concrete example. This is a little bit different than the example in the Markdown document, because I wanted to give you guys several different examples in which you can think of this workflow. But this example is one we talk about in the paper that some of these slides are based off of, that's also linked to there, which is the challenge of estimating the concentration of particulate matter, measuring 2.5 microns in diameter, right? So these are really small bits of pollution, right? That are smaller than the head of a human hair, right? And associated with millions of deaths. And the World Health Organization is trying to estimate the concentration in different parts of the world, right? The problem is that except for small areas where we have really good ground monitor measurements, most of the data comes from satellites and it's really noisy, right? And the quality of the data from different regions of the world is really different, okay? And so here's a little map. The black areas are where there's actually ground monitors. So basically, United States, Europe, some parts of Asia, but like none in Africa, barely any in South America, right? And then the darker the color, the greater the concentration, the measurements, right, of the PM 2.5. So we can see very different levels of coverage of ground monitors, and then the rest comes from noisy satellite measurements. Anywhere there's not a black dot, the measurement had to come from satellites. And so, right, so the goal here is going to be, okay, well, how can we use the ground monitor information that we trust to help kind of calibrate the satellite measurements so that we don't have to trust the raw satellite data, right? How can we use measurements that we know? So some areas we have both ground monitor measurements and satellite measurements, and others we only have satellite measurements. So we want to be able to do a better job of calibrating the satellite estimates based on areas that we know and we can compare the two, right? And so to do that, we might start thinking about, well, okay, what kind of data do we have that helps answer this question? And so the first thing you might do is just look at, first of all, if you're a scientist, you're studying this problem, you're going to have some already ideas about these questions. At least you should if you want to start an analysis like this, right? And so you should already kind of be thinking and studying this problem, right? And then when it comes to actually developing a model to do this, you're bringing your knowledge to the table. We're not just going to look at the data and then back out answers. We're also going to bring to it, right, whatever the domain expertise is, and and that's going to come in different roles in the process. It's going to come in by informing what kinds of visualizations you look at to learn about your data and do exploratory data analysis. It's going to come into play when we're choosing how to specify prior information, right? And then also in constructing the model, the rest of the model itself, right? And so here's just the plot of the raw data that we have here for places where we have both measurements from a satellite and what I'm just going to refer to as the true PM 2.5, which is the ground monitor measurements. And there's a pretty strong, I think if you ran a simple linear regression, you get an R squared of 0.6 or something. So there's a pretty there's a pretty strong linear relationship here, but clearly we could think about different ways. So these are groupings based on the World Health Organization, clustering, whatever they classify countries as. And we can see that there's, we could also allow for heterogeneity in these linear models, right? But this is basically just doing a little exploratory data analysis. I'm just using ggplot and R and telling it to put classical regression lines down. I'm not really fitting models. I'm thinking about what kinds of things should I be thinking about with this data, but I'm not looking at the coefficients for these lines here and making decisions based off them. I'm saying this is data that I could think of as having different slopes and intercepts here, or I could think of it this way. I'm exploring ideas for how to think about the structure of this data, but right now I'm not saying what's the slope of each one of those lines or something like that, right? But you could imagine other ways of grouping the data, which is maybe based on clustering the countries based on their actual levels of the pollutant, right, of the particulate matter. And so if you do that, the World Health Organization ways of grouping countries are just based on like economics and then contiguity. So like it's rich countries, and then everywhere else it's, are you next to some other country? And the regions from clustering here are regions based on the problem itself is based on, okay, can we group these countries based on areas that we know historically have high levels of this, have lower levels than this, and we can, we can make a map like this, and you can see the differences in the groupings there that you get. And then you obviously get some different looking plots here. And so this is just something to think about here, whereas the types of things we're gonna be able to do are really gonna depend on how we're conceptualizing this data, right? And why should we choose like one way of like grouping the countries or another? It really matters like what we care about studying, right? So the point here is that you can't come to a class like this and then learn how to like solve these problems on your own. You have to work with domain expertise in your field. You have to think about, like a statistician can't tell you what is the important way to group countries in your problem or something like that, right? These are things that people in the fields themselves, right, that you're studying have to bring those ideas to the table. All right, quickly. Here's some notation. This is like there's not much more math than this. This is pretty, so I'm gonna index measurements with N and like regions, geographic regions with J here, right? And then you may have seen models, and then we're working with like the log of the outcome variables here. And so the NJ measurement of that variable, right, is it's like the nth observation, and that's from region J or something. And so this is kind of a classical way of writing a linear regression here, whereas we have some intercept alpha and a slope beta, right, on the variable here. So, right, we just have a linear regression here of the XY relationship between the satellite measurements and the ground monitor measurements. Does that make sense? And then this is kind of the way that you might see it written in like classical statistics textbooks, where you have a linear thing and then an error term or something like that, and then that has a distribution. I'm going to encourage you to think about this model instead as if it was this, which is the same exact thing mathematically. Right? If the errors have a normal 0 sigma distribution, then we can just instead give the whole thing a normal distribution centered at this piece here. And this second way of writing the model, I think, even though they're identical statistically, I think looks to me a little bit more generative, or thinking about, okay, how is this model, how is this data, what are we saying about this data, right? We're saying that, and they both are saying the same thing, but you're gonna see us, and when you, in these tutorials, like write things a lot more in this second type of notation than in the first type of notation, where you're really saying what distribution are we talking about for our outcome variable, as opposed to what distribution are we talking about for our errors, right? But again, it's the same model, but it's a slightly different way of thinking about it, where you're thinking about the distribution on, you know, there's this deterministic part, and what's the distribution of the errors, versus thinking about it as, what's the distribution of my outcome variable? All right, does that distinction make sense? Yeah. And so again, you can write them either way you want, but throughout the rest of this conference, you're probably going to see these models written more often using the second notation than the first notation. And so if your background is more classical statistics or economics, right, you're probably more used to the first line. When you see things written the second way, it's really saying the same thing. And so if you see that over the course of the next few days, you can think about it as if they're equivalent, but maybe people coming at it from different backgrounds, just thinking about what the implications of the models mean in different ways. I added this point in after several times of teaching workshops and conversations with people where the people had been coming from backgrounds for so long that they'd actually never seen models like written using the second line, especially if you come from like economics or something. You're really always seeing error distributions. All right, and then just very quickly here, right, we might want to do something a little more complicated where we, instead of like putting the linear regression term here, I just put in a mu here so that I could write out a longer expression that allows that alpha and beta to instead have little offsets based on which region you're from, right? So instead of just having an alpha at one intercept and one slope, we might have like alpha 0 be some, global intercept, and then each country might deviate from that a little bit, right? And that would be the alpha j, and the same might be true of the slope of the line, right? For the coefficient on the satellite measurements, right? That might vary also by region, right? And so we could write a model like this that allows there to be some kind of overall slope where each region deviates from it just slightly or substantially based on the information that we have. Is that notation comfortable for people? Does anybody have a question about the notation or the concepts? We will throw you a box to talk into. Right, and so these are replacing the alpha and the beta that were on the previous slide, right? We're separating them each into two components. One is kind of shared by all regions, which are the ones with the zeros, and then offsets for the different regions, right? And then if we're Bayesians here, which you either are or aren't yet, then we need to think a little bit about, where these, and this will be covered more this afternoon in the hierarchical models class, but it is part of like the workflow that I want to talk about. We're not going to code this model, but this will be more similar to what Ben will do this afternoon, is then we need to think about, what do we know about these parameters? Now, we don't necessarily know that they have a normal distribution, but we could say that like it's a pretty good approximation to what we know, that these are going to have some level of variability, right? And we'll call that amount of variability across from region to region tau. It's like a standard deviation here. So I'm writing out this, instead of tau squared, I'm just writing tau because you'll see that Stan wants the standard deviation instead of the variance. But it doesn't matter. Equivalently, we could have written this model putting the alpha 0 here where the 0 is and pulling it out of the equation above, and same with the beta 0, right? So because another interpretation of the second line, or the third line, the bottom line here, is that these country or region specific offsets of the intercept, right, are centered around 0 and then have some standard deviation tau. But then we're just shifting them over by alpha 0 here, right? So you could center the normal distribution around that instead of shifting it over, right? And so you'll see these models written both ways sometimes. In fact, in the same textbooks by people I work with, you'll see these models written both ways. So I think it's good to see them that way. And then we can say the same thing about the slopes, but we might allow it there to be a different amount of variability in the slopes than there is in the intercepts, right? If we could get estimates of tau beta and tau alpha that are very similar, and we could learn that there really isn't that much difference in the amount of variability there, but we could allow for it, right? Okay. And so just by like kind of thinking about the data and stuff, we've got actually like 3 models here already. One is that simple linear regression, and then we have this model here, which we could fit to the World Health Organization clusters of the J's could refer to the WHO region clusters, or they could refer to the ones based on the levels of particulate matter, right? And we would get different, those are different models. So then I said, okay, we need to check, even before we fit a model to real data, like we can already start to check if it makes any sense. That might sound strange, but for pretty much, I don't think I've ever confronted a problem for which that wasn't true. And the reason is what I said earlier. If you want to really build a true and full Bayesian model, you have to build a model for how the data is generated, right? And there's this prior, there's this likelihood, but really what we care about is the joint of them together. We care about just expressing mathematically the process, the generative. Oops, sorry, this is what I wanted to show you. We couldn't have this class go by without looking at something like this, where, right, this gray box, or greenish gray box here, is what you normally see as the numerator to Bayes rule. You might have seen it as like A given B or something, but here Y is going to refer to like data, stuff that we've observed, and theta is going to refer to anything we want to make inferences about. And what we care about is this joint distribution of Y and theta. That is, what is the probability distribution over all of the things that I know and that I observed and that I want to make inference over together. And then we can use probability theory and decompose that in different ways, right? We can write that as a likelihood times a prior. That's just, terminology that you'll see, but those are the distributions they refer to. Some distribution over the unknowns, the thetas, where that comes from, we're going to talk about, right? It'll be based on knowledge of the problem, and then some distribution for the data that you observed given values of those unknowns. And then we can kind of switch it around, and you can just call these, right, there's all sorts of jargony terms here, but the idea here is conditional probability works, right, where we can flip these around. And so we can write this stuff in all these different ways, and so how do you know like what's a useful way to think about it, right? These are not all going to have, these are all equal statements in probability theory, but some of them are more useful to the modeling process than others. Specifically, this last one here is kind of useless to us right now because kind of finding the posterior is the whole point of this thing. For Bayesian, right, we want to find the distribution of the things that we want to make inference about given the data that we observed. What should we think about the parameters, the unknown quantities, after we've observed our data and updated it, and that's the posterior distribution. And so writing it like this doesn't really help us because it's using something that we're trying to find, right? But if you write it like this, we can express those things based on our domain expertise and knowledge about the world. And so you always just kind of see it written down, maybe like this, at least the numerator in textbooks. But it's exactly equivalent to this here, but this would be a completely useless way to think about it until you had a posterior distribution, Right? But these are all actually saying the same thing. And so it's not a given that you, right? So you have to think, well, what information do I have, right? Well, you might have some information about the unknown quantities that you're estimating. You might know ahead of time, well, it's unrealistic for this thing that I'm trying to estimate to be in the trillions, unless you're dealing with like debt or, I don't know, other things, right? And so even in situations where you don't have like a ton of precise information, you kind of generally have some sort of information, and so that comes in this P of theta thing here, right? Things that you're bringing to the table ahead of time, and so we know something about that, right? And then we can, based on our domain expertise, we can come up with a model that says, okay, if I knew those underlying quantities that I'm trying to learn, I don't know them, but if I did, right, how would that result in different kinds of data? What would the distribution of the outcome be based on, the value that I knew of? So in our case, you could think, what would the distribution of like the satellite measurements or of the ground monitor measurements be if I knew the slope and the intercept, right? Or something like, or what would the values be if I knew the slope and the intercept? But of course, you don't know the slope and the intercept, and so for each possible value of the slope or the intercept, it's going to produce different types of different data, right? But this P of y given theta is just, in our case, in our previous case, that's the linear model, right? This P of y given theta is we're saying that the outcome variable, now we could have an x in here too, y given x and theta, so you could have predictors for y, but we're saying, okay, we have an outcome variable, right? And we have some unknowns like the slope and the intercept, and then we have some maybe predictors like the satellite measurements. And that had a normal distribution, right, with sigma standard deviation, right? That's the P of y given theta in our case, that line that said that like the ground monitor measurements were distributed normal, centered around the alpha plus beta, right? And then what we knew about the slope and intercept ahead of time is that P of theta. And so if we write it this way, we know things about those two terms, right? And then that's what Bayesian modeling is going to be founded on. And what we're interested in eventually finding is this posterior distribution here, right? And yet both of those quantities there are actually pretty hard to calculate, and these we can just specify. So I know this is a little bit strange, but I wanted to make the point that it's not obvious that these are all true, but you have to think about like which way to rearrange these terms is useful to me, right? And in our case, useful to statistics in general or inference, right? But that's the same in your particular modeling problems. Which way of grouping the countries is useful to me, not like is better overall or something like that, or which way of specifying the relationship between the unobserved and observed quantities. There can be various equal ways of expressing those, but some might be more amenable to computation than others. There's going to be all these reasons to prefer one version of kind of an equivalence to another. Right, and it's kind of strange. That's going to come up. You'll see this afternoon that there are like statistical models that you can write down that are identical to each other, and there's reasons to prefer one to another for computational reasons. And so we're kind of making all these decisions along the way, which terms we're going to look at, which model we're going to pick and sometimes they're going to be equivalent, and it's just rearranging things or writing it slightly differently is going to open up like a more useful approach. Okay, and then before, we're almost ready to start coding here. But the last thing here is that, so I'm going to tell you, I'm going to give you a visual example of why you can tell before you fit your model that it's a stupid model. Okay, so, and this relates to this idea here is, so there's something called an improper prior where you're not really specifying a proper probability distribution, but you don't even need to worry about that for a second. Just any sort of distribution that we decide to use for, like, in our problem, like the slope or the intercept in that regression problem, or in more complicated problems expressing complicated prior knowledge about that. Any distribution that we choose could be pretty informative. It could be, we could specify a distribution that encoded a ton of uncertainty. You can even go as far as saying, it's just flat, which is often technically not a probability distribution if it's not bounded, right? There's all these different ways, amounts of information and different things we can express here, but oops, I'm sorry. But the idea here is that there was an old-fashioned idea that we shouldn't bring much of our prior knowledge to the table, and then we've started realizing over time that that makes absolutely no sense because we have a whole bunch of knowledge to bring to the table, but also that there's other things that priors can do, is they can help avoid overfitting. They can what's called regularize your inferences, right? Give you more of a compromise between being super sensitive to the particular data set you observed and being too much tied to particular amounts of prior knowledge to find some trade-off in there, right? And if you kind of take the old-fashioned approach of we want to kind of just use really wide priors, maybe a normal distribution with a variance of 1,000 or something, or more than that you'd see, you're really, if you do that and you don't check what are the implications of that, which people didn't used to do, then you can end up finding you can end up in really strange situations that you're not even aware of because you never looked at this. And this is this, idea of prior predictive checking. What I want to focus on here, if we specify a prior, then here's what we can do. We can simulate a value of a parameter. I'm just using theta for a generic parameter here. It could be a slope, or it could be an intercept. It could be, right, the alpha and beta from before, but this is just anything, right? Whatever it is, it could be, let's say we have a normal distribution that represents our uncertainty in the intercept in the linear regression model from there, right? We could simulate a value from that normal distribution, right? And then we could plug it in. We could plug it into the linear regression, right? That's what this P of y given theta, the likelihood, the model, right, is that we had a normal distribution with alpha plus beta times that, right? We could plug in the simulated alpha and the simulated beta as the values of alpha and beta there, right? And then we could simulate a value for the normal distribution of the outcome, or in our case, of the particulate matter measurements, right? We could simulate those if we knew the value of alpha and beta and sigma of the normal distribution. Then we could simulate from outcome values, right? And what that amounts to, that two-stage process, amounts to sampling from the distribution of the outcome unconditionally on the parameters. So as you start to repeat these simulations over and over again, right, you start to build up what the distribution of the outcome looks like, but now you've averaged over all these, you've simulated a whole bunch of different intercepts and slopes, and you can see the different implications that they have, right, for different types of different simulations of the outcome. And we have what's called a prior predictive distribution. That is, what distribution, right, is implied for our outcome variable based on our choice of prior and likelihood here. And then you can plot those things, right? We can plot those simulations, right? And we'll see in a second that if you don't do that, if you don't look at what that is, then you might be using a model that is completely implausible before you've even fit any real data. So, for example, let's say in our particulate matter example, we used some pretty standard non-informative priors here. So let's say we said that the part of the intercept that was shared, that was common to all the regions, had a normal distribution with, again, that's a standard deviation of 100. I'm using the Stan convention here. And then these inverse gamma things, if you don't know what they are, don't worry about it. It's a very old-fashioned choice of prior that was, the only thing you need to know is that it used to be considered non-informative. It used to be considered vague in some sense. And then I simulate some data, and I plot the simulated data against the actual observations that I have, right? Now, I don't even have to do this. I could just look at the simulated, if I had enough expertise in this problem, I could just look at the raw simulated data, a histogram of the simulated data. But for our purposes here, I'm just showing you what it looks like, because you're not all, neither am I, experts in what this kind of particulate matter data looks like. So I'll show you against the real data. But so on the x-axis here, we have the actual, don't worry about it. It's okay. You want to answer it? It's okay. That happened to me my first day of grad school. Okay, so on the x-axis we have the measurements that we have, the data that we collected, the ground monitor measurements of the particulate matter, and on the y-axis are the simulated values from just the model by simulating from the prior distributions and then plugging that in to the linear regression stuff and then simulating values for the particulate matter. And so, right, you might notice that these should look similar, by the way, that the simulated data has a order of magnitude that's 2 orders of magnitude different than the actual data, and that's on the log scale, which is just an enormous difference. Now, maybe in some cases, if data that different from the data you observed is plausible, right, in your particular area, then that's okay, right? But in this particular case, everyone would be dead if we had levels of particulate matter on that level. And so if we used priors like this that result in such outrageous distributions of outcome variables, right, then we're going to have to overcome that misspecification in some sense, right? The data is going to have to be strong enough to overcome that ridiculous choice. If it's not, and in our case we do have somewhat noisy data for these measures, if it's not, then your subsequent inferences are going to be highly potentially affected by just a kind of ridiculous choices that you could have noticed immediately if you just simulated from your priors, and right? But rarely do I see people saying that they've done this when they publish stuff. They check posterior stuff, but they don't check here, right? So let's compare to what that looks like if we make some more sensible choices, right? So, okay, what's this? Instead of normal 0, 100, now based on domain expertise, right, the people who actually study these problems can come to you and say, well, yeah, the satellite measurements are noisy, but they're pretty decent, right? And so we might say that we'll start with the prior of an intercept centered at 0 and a slope centered at 1, an alpha of 0 and a beta of 1. just saying that like our prior is that it's a reasonable linear relationship, but then we're going to allow ourselves to be wrong by having, in this case, even just a standard deviation of 1 here is enough to allow us to be wrong about that intercept and slope. You'll see in a second that that actually allows for a lot more variation than you might think. And then what I've done here is instead of those weird inverse gamma distributions, I've just said let's use the positive half of a normal distribution and have it be normal 0, 1 here for these parameters. And the data it simulates looks something like this. Right, so again, this is the actual observed data, and this is the simulated data that's supposed to, look plausible. And here, right, we still have, much larger simulations than actual data points here, but that's okay. Like this is much more reasonable, right? We've allowed our simulated data covers all of the actual observed data plus more, right? It goes we get much larger values. And so actually, even going up to 10 here, like on the log scale, is pretty implausible in this problem. But so we could maybe even constrain that more just based on scientific knowledge, right? Not based on the data that we collected, but based on just scientific knowledge. But this is much more plausible. And so, oops. And so to bring that point home, if you were to plot them on the same plot, the plausible data would kind of look weird. It would just be crunched down at the bottom here because the implausible data would make us put the y-axis up all the way to 800 or something. But so this is what we call like a weakly informative prior. I use that information that, scientifically from previous research or just people studying this problem, that the linear relationship was a plausible prior, a slope of 0, intercept of 1. And so I used like a weak amount of information. I didn't say I'm going to center it really tightly around 0.739 or something like that, right? And then the non-informative prior is up there, and if you plot them on the same plot, it looks like this. And so there's no reason why you can't make these types of visualizations when you're working on things to think about, does my model make any sense before I've even started? You can go. Maybe you should get a little closer.
Okay. Really excited for this. Okay, great. My question was, by plotting it relative to the observed data, right? You're kind of already doing some estimation from the non-informative to the weakly informative.
Yeah.
You kind of updated your non-informative prior with your data to get to a weakly informative.
Right. So I was saying a second ago, if you were really if I were or you were really a domain expert in this area, you could just look at a raw histogram of the simulated data. You didn't even have to look at it compared to the observed data, and you would know that it was implausible. But I'm not an expert in that field, so I wouldn't be the person, making that plot, and like you would, right? So in your field of expertise, you wouldn't even have to necessarily compare it to the observed data to know that it was totally implausible and motivate changing your prior, which would not mean that you had updated your prior based on observed data. It would mean that you had updated it based on your domain knowledge, right? So simulating from your priors and saying that's ridiculous is a way of using your domain expertise to start narrowing in on what a better model is. But yeah, if you do too much of like, what does it look like compared to the particular data set that I observed, then you could start to overfit here, which is why if you do compare it to the data you actually observed, you want to make sure that your prior predictive distribution includes all of the data that was observed, but not only that, all plausible data sets should have some positive probability, right? And so yeah, you do not want to simply based on the data that you observed say, I'm going to tighten up this prior predictive distribution until it looks super similar, right? It should really be based on what you know is plausible. And in this case, it was more of like a demonstration. Does that make sense?
Yes.
All right, cool. Good question. After these questions, we're done with the slides for now, and we'll start doing some coding before the coffee break.
Excellent. Okay, thanks for the tutorial. Maybe I missed here something, but because previously you had on the x-axis you had the what is observed on the Earth, and the y-axis is what's observed from the satellites, like right at the beginning. And now you move towards having it on the x-axis, the simulated Earth. No, probably the simulated.
Do you mean
satellite.
here?
Yeah.
Yeah. So here I'm showing the noisy satellite measurements against the, but I could have flipped this either way, against the ground monitor measurements, and then the later ones are the ground monitor measurements, so those, against simulated data from the model, seeing if it looks at all plausible, right? And so this x-axis here is not plotted on the other one. The satellite measurements are not plotted. I should have made that more clear.
It's okay. Okay, that makes it a bit
So
clearer.
here, now when we get back here, right? So in our model, so this is a good question, and I think I see what your question is. In our model, the satellite measurements are serving as a predictor and not the outcome. And so when I talk about doing these simulated things, I'm talking about simulating the outcome, and that's the ground monitor measurements, like in our model, right? And so that's why I was showing those here and not the other ones, even though before it was on the y-axis. Does that make sense? Because this is the outcome in the model.
It nearly makes sense. I need a cup of coffee, and then it will probably work.
Mm-hmm.
Does data help? So if I have a non-informative prior and I have zillions of tons of data, so does it then, let's say, wipes this problem away?
So this is wait. Right? You could be in a scenario where your data is strong enough, right, to overcome the prior. In this case, you're not. In a lot of real-world situations, you're not in that situation. It's true that sometimes you might have an overwhelming amount of informative data, and you can overcome poor choices of prior distributions, right? The theory is that even if you start with a stupid prior, eventually, if you learned enough from data, then you would move towards a better answer, right? Of course, that requires having some sort of sensible model, but yeah, you could be in a situation where you could specify a poor prior, and the data would help you out there. But I want to caution against thinking that just because you have like 1 million or 1 billion observations that you have highly informative data. There's a difference between the number of observations and how informative that is. You could have 1 billion noisy data points that are less informative than 100,000 really non-noisy data points, right? So it's more about how informative the data is as opposed to just the raw number of observations. But certainly more good data will help avoid problems like this.
Yes, so my question was basically the same. So you would not advise, again, I read often that when you have enough data, you can basically skip worrying about priors, so that is not a good idea, in your opinion.
Maybe can we turn up the
Yes.
volume on that mic?
I would speak a little louder. So my question was basically the same. So just, I read often that if you have enough data, you can basically skip worrying about priors, and that is not a good idea in your opinion.
Right, yeah, I disagree with what you've read a lot about, which is that if you have enough, well, I don't disagree with it, depending on what you mean by enough. If by enough you mean enough very informative data of high integrity and whatever, then sure. But typically even large data sets are pieced together from different smaller data sets, and they have different amounts of variability. Like a lot of times you might have big data sets that when you try to answer complicated questions using them and you start slicing them up in different ways, you actually end up with much noisier data than you started with. So So yes, but if you have enough of the right kind of data. It's not just the size, right? As the number of observations goes up, that does not guarantee that you will overcome these problems, well, if you go infinitely long. But otherwise, it needs to be informative data. These are good questions, though, because you do read that a lot.
So I was wondering how concerned you are about the homogeneous spread of the simulation. So going back to your weekly informative prior, yep, that one there. So where the observations are at about 4.5, it seems to be a bit of a bimodal spread with a bit of a gap at the one-to-one relationship. So is that something that would concern you, or?
Here?
Yeah, so there's a bit of a hole there.
Yeah, it doesn't really concern me. So what I'm seeing here, what I'm mostly looking for here is some sort of that the plausible data sets are covered. So what's happening here is and we could look at a different visualization of it, right? Right, most of the observations are coming right here, and then there's enough uncertainty that you're just getting kind of splotches of them out there in weird ways. And I'm saying yeah, even some of those are probably implausible based on scientific knowledge about the particulate matter stuff. But in this case, at a minimum, at least we're covering all the plausible bases, and then yeah, we're getting some, because there's enough variability, we're getting some extreme draws that are kind of give you those splotchy areas out there. But yeah, you can check different visualizations that give you a different perspective and make sure there's not some really weird pathological thing going on. But this doesn't look too bad.
Okay.
That's a good question. Now I'm wondering if this is any more effective than walking around with the microphone. But
my question is, this is like a good sanity check, I guess. If you see something ridiculous, you know that those priors are not good. But if they look plausible, that doesn't necessarily mean that you pick the right things, right? Because you could potentially, okay, with 1,000 standard deviation, unlikely, but you could still sample something that makes it look reasonable, even though it's not.
yes.
So would you recommend doing it a couple more times?
Yeah, and what we say in the paper that this is based on is you can kind of make a flip book of these, right? You can simulate a lot of them, a lot of different pictures, and cycle through them, and you'll get a sense for all the different data sets, well, at least many of the different data sets that these priors could result in. This is one of those, but you could, just in a loop have it do it 1,000 times or something like that, and it will give you different data sets each time, and then just have it quickly cycle through the images or something, and you'll get a sense for, you could do that dynamically, even all the different types of data that this prior is implying. Yeah, so I would do this, this is just one of possibly many.
Okay, thanks.
It's a good question.
Does including features change this process in any way?
Does including the pictures?
Features or predictors?
Oh, predictors.
Yeah.
Does including the predictors? No. So in this case, the simulated data comes from that regression model where the predictor was the satellite measurement, but you could have any predictors that you want. They're not being simulated here. They would just go in, you would say those are known values like the parameters that you simulate. Now, for more complicated models, where certain independence assumptions are not valid, then you would need to simulate predictors also, if there's certain correlations or something, but not according to the model in this case. The predictors just would go inside the alpha plus beta times x part, and x could have as many predictors as you wanted in it. Is that? Yeah. We have one down here afterwards. I mean, if there are lots of questions, that's great too. We can just go until the break, and then after, there's a break at 10, I think, right? So we'll either just keep going with questions until then, or we can, I don't know if we'll have time to start the coding before then now, but I'm happy to keep answering questions, and then we'll come back and start the coding.
Okay, my question is that even though we have this afternoon decision about model selection, might be possible to see if you have done a poor prior selection by applying one of these criteria for looking at how good is your model for predictions?
Do you mean like looking at information criteria or something?
Yes, exactly.
Yeah, so Aki's going to talk about that this afternoon, but yeah, that's an example of a way you can compare models after fitting them, right? So here we haven't actually fit the model. We've just said, what are the implications of the model, right? And then once you fit the model, which we'll write some code and then fit a model, then you could start calculating things like that. And so that would be part of the model comparison, part of the workflow. So yeah, if you're around this afternoon, Aki's gonna have a workshop on that. But yeah, absolutely, that would be a valid way of comparing these models after fitting them.
I feel like Jonah and I should have switched jobs for a little while.
And the reason I took so long on this topic really is that I think it's of much greater importance than it gets. Like, people are, trying to, we get, I'll come to your question, we get a lot of questions on the Stan mailing list from people who are fitting all these complicated models, and they're asking, like, why isn't this fitting well? Like, why doesn't this, why is this broken, why is that broken? And very often we're like, well, have you simulated fake data and looked at it? And then they'll do that, and then they'll come back and they'll be like, oh yeah, that they'll see that it doesn't look anything like they're expecting, and then they'll look and they'll find some either mistake or some misunderstanding about what distribution they were using or something like that. So this is just not just for checking your domain knowledge or something, but just checking that you've coded your model correctly even, right? I can't emphasize enough, like I would do this every single time, right? It doesn't matter what the application is, you can always do this. That's the whole point of these models, is that you can always simulate from them. And so there's no reason to be running around using any models that you haven't done that with, right? Otherwise, you don't really know what the implications of your model is. Unless even the most brilliant statisticians, once you get past very simple models, they're not going to be able to tell you that either. They're going to have to do this and look at the process. It's not just something to do until you become, good enough to not do it. It's something to do forever, unfortunately. Yes, so.
Hi, yeah. If we look, for example, at the beta, let's say we know it can never be negative. Is there a way to include that?
Say that again?
Is there a way to say that beta, for example, can never be negative? Let's say we don't really know the slope, but we know it can never be negative.
It can't be negative.
Yeah.
Yeah, so then, right. So then this would not be the right.
So you just have to take another distribution. You cannot give a restriction in the normal.
Well, so we'll see with Stan that you have a little more flexibility, that you don't necessarily have to choose a distribution yourself. That's always positive. It can help you, like, cut a normal distribution in half or something like that. But yeah, if you wanted to encode that beta had to be positive because that was some logical requirement in your field or whatever, then yeah, you would choose a distribution that only had positive support, or do some sort of transformation, like model beta on the log scale and then exponentiate it after or something like that. But yeah, so you would encode that information also, and that could come just by saying it's very likely to not be negative, which is, you could maybe shift it further. But if you want to say it can't be negative, yeah, then you'd have to explicitly encode, like use a distribution that's positive, or transform it. Yep. Any other more questions?
Right. So I was just thinking earlier, someone asked about having lots of data. So if you do have a lot of data, but you don't really know the domain particularly well, or maybe even you understand something about it, but your model is so complicated that just like, the prior might be complicated, or the priors. So would it make sense to, if you really have a lot of data, to use a part of the data to and estimate the prior from that, And then, as long as you don't use that part of the data for inference, then of course.
Yeah, it can make sense to do that. I don't know. It's if you're able to. Yeah, it really depends on if you're in a situation where you are able to keep collecting more and more data, then
right.
Yeah, then I would say keep updating your prior as you go along. But if you're just able to collect a big data set, I wouldn't. Some people might have different opinions. Some people might say, yeah, just mess around with the subset of it, and then fit on the rest, testing, training, kind of stuff. But it really also depends on if you're in a situation where you have enough information to bring externally, or if you don't, or it's hard to give unfortunately, it's hard to give like a yes or no answer to that
so
question.
It depends.
It's super context dependent.
Yeah, I guess you might sometimes you might have some sort of prior knowledge.
Yeah.
Basically, for example, you know that, I have this parameter and I think the data, or I have a reason to believe that it's pretty homogeneous, that I have like 1 billion observations and, maybe I'll get 1 billion a week or something. And I have reason to believe that the distribution is pretty homogeneous, but I don't actually know what the parameters are.
Right.
So in a sense, it seems almost more honest in some sense to, use some part of your data to estimate what the distribution is roughly. And then, of course, set aside that part of the data, to avoid double dipping and overfitting.
Yeah, you could do that, or you could just use a prior that, wasn't so horribly vague, but was, a little wider than what you would have used otherwise, and count on, like, if in this case your data is big and informative, that will be sufficient to learn those parameters anyway. Really, yeah, so it depends on how informative your amount of data is, if you can get away with kind of not expressing any prior information or not, or whether or not you want to. But yeah, sure, you could imagine it as if you collected a preliminary data set to study with, and then develop something and then not use that data when you fit your actual model. That's possible.
Because in a sense you're doing something a little similar here, but more heuristically. Because you're comparing your simulated data with the real data, and saying if that makes sense. So in some sense you're still using the data to figure out what your prior should be. So
that's right.
I guess I'm just.
Like I was saying before, you want to be very careful here that if you do use your observed data in these comparison plots, that you're not too closely making your decisions, but that all you're saying is that my simulated data was sufficiently broad to capture the actual data that I observed, not that it looks exactly like the data that I observed, but isn't so broad to include data sets that I know are either physically impossible or theoretically impossible or whatever. Right? But yeah, ideally, if you have enough expertise, you don't even have to compare it to your observed data. You just can look at the simulated data and say that's ridiculous. And then in what way is it ridiculous? Is it consistently too large? Is it consistently not variable enough? Is it, right? And that will inform, better choices.
Thanks.
That makes sense, yeah. I can hear you, and then I can repeat your question so everybody else can. I would call that a small model. Right. Yeah, this is a good question. So in case people can hear, the question was like, if you have models with more parameters than this that have different types of dependencies in them, can you still do this, or how would you go about doing this in a sensible way? So then if this was more complicated than this, then you could, there's all sorts of ways it could be more complicated. So sometimes you have models where you can simulate data at like an intermediate stage of the model. You might have multiple outcome models. And then you could simulate data at different stages and make sure each part of the model looked reasonable. If it's just a bunch of complicated parameters affecting one outcome, then what you can do in these sort of simulations is alter the priors on those, keep the priors the same for, a bunch of the parameters and change the ones on ones that you're interested in knowing about what role they're playing. So this is a way to explore, because it's just simulated data here, if you forget about the observed data for a second, with simulated data, you can do anything you want. It's just learning what your model is all about, right? You can set ridiculous priors just to see how ridiculous the data gets from the ridiculous priors. You can set really highly informative priors to investigate, what does your model say when you do that? You get to do whatever you want. You're just doing simulations, right? And so so you can isolate by saying, okay, I'm now going to change the prior on this particular group of parameters and keep the prior the same on all of those, and then do simulations, and then you'll start to learn, okay, what role are those guys playing because I'm changing those parameters and keeping the other ones constant, and then you can, right? And it is tricky because ultimately the only way you observe how all of these things come together and interact is in the outcome distribution. Right? Because that's the result. But you can do some things to try to figure out how are certain pieces of the model playing a role compared to others by changing things about those in simulations when not changing things about other parts. And this is a really good way to just interrogate the models that you're developing. Like, what do these mathematical objects say? Right?
I think the other thing in that is that you're not actually fitting the model, you're just simulating the data, so it's a lot quicker than fitting.
Oh yeah,
like
this is super
fitting
fast.
parameter.
I'm not doing any MCMC, any Markov chain Monte Carlo. You're just using if you're using R, you just use R norm, the norm, or in Python, whatever, any random number generators, right? I only need to use the Markov chain Monte Carlo when I want to do inference. But the rest of it, just that, I can just take independent random draws from each of these. I can simulate all this data in, I could do it right now a million times, maybe trillions times. I don't know. Not trillions, definitely millions, right? Yeah, so that makes it feasible to do this for even complicated things, because at this stage, we don't have to fit the model every time.
I guess I think one thing that I would add is oftentimes people will tell you that they don't know anything about the parameters that they're interested in, or they don't have any prior knowledge, but even with back of the napkin estimation, you can get a good estimate. So this, it's really clear, because if the parts per million goes over, was it 8,000? 800? Then we'd all be dead. But
oh yeah.
Later on we'll look at cockroach data and the number of complaints of cockroaches in apartment buildings, and that's our example, because we live in New York. And so you can say, oh, we don't know how many complaints there will be, but realistically we do. We know that's probably not going to be more than the number of people in the building complaining once a day, and that kind of sets a kind of rough cap. And if we're estimating a lot more than that when we look at our simulated data, then we know that maybe the prior's just a little bit too weak.
Right, yeah. If you're simulating that people are complaining enough about these things that they don't have ever time to do their jobs, then there's probably something wrong with your model or something.
Yeah.
So it's all about interrogating the different parts of your model and making sure they make some sort of sense before you're going to throw it out there at a real challenging problem with consequences for, I'm sure some people here are working in very consequential areas that impact a lot of people. And I get really worried when I see research that comes out and people haven't really gone through the steps of interrogating their models and really understanding the implications.
I have a question about the, do we also include the outcome distribution during prior predictive checking? For example, if the outcome is a normal distribution, do we also include that here while simulating?
Right, yeah, so that's how, right, yeah. So these were just some of the priors, but yeah, then we would feed those values into here. And then simulate from the normal distribution. Was that your question? The distribution of the outcome here was the normal distribution at the top line, right?
the observed estimates, right? Like
No,
we do
right.
not fit
We're
them.
not using the actual values in the simulations where, right, those pieces right there would not be, those are being simulated. We're not actually plugging them in, yeah.
Okay.
Right, that's right.
Thank you.
Yeah, you're right.
So behind you.
Did that answer your question? Yep, so that's what we're trying to say, like, can we simulate data that's at all plausible before we try to fit this model to the observed, the actual data? Yep.
Okay, now how do we choose the log sat in this case, continuing on that question?
How do we choose that it's on the log scale?
No, the measurement, the satellite measurement, do we just sample it from the data or?
In the simulations?
Yes.
Yeah, that's, so yeah, here I was just using the actual observed, the measurements for that, because it's not what we're modeling. It's the predictor, then yeah, you could just plug in the actual values. But in other cases, you might want to plug in simulated X values or deterministic X values that are just ones that you're curious about what the model says at the values of those predictors, right? Again, here we're just simulating. So if you want to say, you know, what are the implications of this model with these priors for super large values of the satellite measurements, or, right, or for whatever variable it is, then just set them to super high values, right? So in the plots that I was showing you, it's like, okay, if we had the same measurements of the satellite and these priors, what would our ground monitor measurements, the relationship be? But we could, right, we could have said, forget about the actual satellite measurements. I want to look at really small ones and really big ones. That's fine too. So it's whatever is important to explore. You want to aim at this guy? Hi.
Hello. How would you, if you have a massive amount of data, like sensor data, and scientists have used millions of years of cleaning that data, could you use some method skipping the cleaning part, so you know that the distribution of the sensor data should be like log normal, but for some reason there is always some negative values. So could you use some method so you make a value prior, even though you know that it should be always like positive, but you want to overcome the prior belief, and it may be possible that the satellite is somewhere else, or the latitude, or some other like 30 things. Is there some general rules when you can, when you are sure that you overcome the prior?
No, but you can explore that in simulations. It's really going to depend on, the last part of that question is there a way when you can know that like you have enough data to overcome like bad choices of prior or something like that? Not really. It's going to really depend on the particularities of the model and of the particular distributions, the interplay between these things. But you can explore that in simulations, right? You could simulate data sets that look something like the one you have with different amounts of noise at different levels and see, right, not your real data, right, but simulate data sets that are somewhat similar to your real data, but then vary, you know, the number of observations, how much noise there is at different in your observations, and see and then choose like ridiculous priors and see what kind of estimates you get. Again, all using simulated data, but it's like it's by far the most powerful way to figure out like what are the properties of this model, not necessarily theoretical, but like what does this model do, right? What kind of data is enough to overcome the prior? I don't know, but I could simulate it and simulate under a bunch of different scenarios and see what happens, right? Before I've even fit the model to the real data, right? Because before I go and these are really powerful tools, but they need to be applied with care. You can't, right? We see people taking all these, just throwing complicated tools at hard problems, right? Just assuming, hey, I have a lot of data, it's going to sort itself out or something like that. But you're right. I think it's hard to know when you have enough data to not worry about bad priors. You always need to be investigating these sort of things, using your domain expertise, and you need to do it like for every problem you do, because it's going to change unless you're kind of doing the same thing over and over and over and over and over again. Anytime you do something new, you kind of have to learn how these things are working in that new context, right? When you fit a different kind of model to different data, things change, right? Is there non-linearities that's going to affect all things in weird ways? But it's easier to learn about those things through simulations than it is through math, because that's the alternative. And I really don't like doing that, so.
Are generative models always Bayesian? Is that what makes it Bayesian? So like if I simulate from a distribution.
I guess it's coffee break time. Let's ask that question, because I don't want to keep everybody else from the coffee. It's a great question. Let's come right back to that one, and then I can prepare the answer.